So in this video we're just going to look at the point of inflection and concavity, and it's often one of the easier marks that you can get in calculus, because we know that to get the where it's concave up, it's just the double derivative is bigger than naught. If we want the point of inflection, we just make the double derivative equal to naught. But just to explain a bit more about what it is and how to interact with it between the different graphs, the point of inflection on a cubic graph is basically where the graph changes its concavity, meaning that it shifts from curving upwards to curving downwards or vice versa. This is the point. This point is important because it represents a balance point where the rate of change stops accelerating in one direction and it starts accelerating in the other. It doesn't necessarily mean that the graph has a minimum or maximum. And so if we want to work this out, we're just going to do the derivative, the first derivative, and we'll do it the quick way now. Times the power by the front and drop it by 1. Times the power by the front and drop it by 1. Times the power by the front and drop it by 1, and the constant term falls away. And if we want to get the point of inflection, or let's just, for sake of something different, let's say we want where it's concave down, it's where the concave down would be double derivative is less than naught, and so we're going to take the derivative here and derive it again. Times the power by the front, drop it by 1, times the power by the front, drop the power by 1, constant term falls away, and so we are left with x is less than 1. And just to show you with a quick drawing, which I've done in one of the other videos, if I wanted to know what does the derivative graph basically look like really quickly, the x turning point of an original graph is the x-intercept of the derivative graph. And so the x-intercepts here are, the x turning points are -1 and 3, and those will be the x-intercepts of your derivative graph. This graph is going in an upwards direction, it's positive, and so we know that the derivative graph will also be a happy graph. So it will be a happy parabola doing something like this. And just to continue the example and link it up to concavity and the point of inflection, if I did the same thing pretending that the parabola I have here now is my original graph, then the x turning point of this parabola, which will be halfway between the x-intercepts 3 and -1, so that would be at 1, that would be your turning point, and your x turning point of this parabola would be your x-intercept of your, in this case, double derivative, and the parabola is a happy graph, and so the straight line would be a happy straight line going upwards. And so what have I worked out in this exact example where I've been looking for concave down? Visually, it's just where the double derivative graph, this green one, is below the x equals y equals 0. So that's what we've worked out with concave down, where the double derivative is below 0. And here you can see a visual representation of it. This value there is just 1. If you found this video helpful, please subscribe to our channel. Please like the video and share it with your friends.